The upcoming demonstration will showcase the process of grilling a steak. The steak is prepared in 3 steps, which are broiling, cooling, and finishing inside an oven. Broiling is done by having a grill plate touching the surface of the steak for a really short period. After this, the steak is cooled in the ambient air until it has a homogeneous temperature that is equal to that of the ambient. If this is the case, the last step will take place, where it is put into an oven until it reaches a core temperature of 25 degrees Celsius. Relevant temperatures, properties of the steak, and the heat transfer coefficient inside the oven are already given. In the first task, we are asked to determine the time required for the broiling process. Broiling is done when at location 1 the temperature reaches 250 degrees Celsius. At the beginning, the temperature is homogeneous and equal to that of the ambient, and also heat will never penetrate to the center of the steak. To determine T1, we need to know the temperature of the steak as a function of the time and position. To find this, we have to solve the heat conduction equation, which we have to determine by setting up an energy balance for an infinitesimal element within the steak. We know the general expression, so let's first make a sketch of what the balance will look like. Heat will be conducted from the hot plate to the inside of the steak, but as the temperature in the positive x direction will be lower, heat will leave the infinitesimal element as well. Furthermore, at the surface the steak will heat up, which means that the temperature increases. If we observe a change of temperature over the course of time, it means that the internal energy of the steak changes over time as well. This yields the following energy balance for our case. Now we need to find specific definitions for all the terms that we just wrote down. The incoming rate of heat transfer can be described by Fourier's law. As we are dealing with an infinitesimal element, the temperature becomes linear within this domain, and we can approximate it by using the Taylor series expansion. So if we plug q.x in, it will look like this. And now we need to find an expression for the change of internal energy over the course of time. For the steak, the internal energy equals the product of the mass, the specific heat, and the temperature. For the mass is the product of the density and the volume, and in our case, the volume is the cross-sectional area multiplied by the infinitesimal distance dx. So now we've found all these terms, we can take the energy balance and plug them in. And if we do some rewriting, our final expression will look like this. To solve this equation, we need one initial condition and two boundary conditions, as the temperature has been differentiated once with respect to time t and twice with respect to position x. A good idea is to make a sketch of what the temperature profile will look like as a function of x and t. Initially, the temperature in the entire body is equal to that of the ambient temperature Ta, which represents this thick line. Then, if we start broiling, the temperature at the surface will be equal to that of the grill plate Tp. Further away, it will decrease with a curved line because the raise in temperature is the highest when really close to the surface. Eventually, when moving even further away from the surface, it is still equal to that of the ambient, as heat has not penetrated far enough. If time moves on, the temperature within the steak will even raise further. So from this sketch, we see that initially, in the entire steak, the temperature is equal to that of the ambient. Once broiling starts, the temperature at the interface will always equal Tp. As heat will not penetrate to the center, we can consider it to be a semi-infinite body. So at an infinite distance away from the interface, the temperature will still be equal to that of the ambient. And now, if we have all required conditions, this differential equation can be solved. Solving this equation is a rather complex process, and the derivation can be found in the lecture notes. But also, the solution is already given on the formula sheet, so we don't need to do the entire derivation, and we can just pick the formula from the sheet. The first thing we now need to do is to determine the value of the dimensionless temperature. To determine the time at which position 1 reaches 250 degrees Celsius, we should plug the temperatures of position 1, the ambient, and the grill plate in, which yields a value of 0.29. Now we know this, we can rewrite the expression at the first line, and we can free up the time. So we find that the error function of the term inside equals 0.71. And as the error function is just a standard function, we can look up what the term inside should be, and the tables used for this can be found on the internet, which yields that the term inside should equal 0.75. With some further rewriting, we can get T3. We don't have the number A, the thermal diffusivity of the steak, but it's basically the thermal conductivity over the product of the density and the specific heat. So we can plug this in and determine the numerical value of the time required, which yields to be 18 seconds. In the second task, we are asked to find the time required for finishing in the oven. The steak starts at a homogeneous temperature again, which is equal to that of the ambient, and it is put into the oven. The meat is done when the core reaches a temperature of 59 degrees Celsius, and heating only happens exclusively by convection, so we're not dealing with any radiation. To find this time t, we need to know how the temperature profile will look like over the course of time. To find this, we have to solve the governing energy equation again, but the first three steps are exactly the same as for task 1, so we quickly skip these. As you can see, the balance is the same and also the definition of these terms, which yields the same differential equation as for task 1. But now we get to the fourth step, which is determining all the required conditions for solving this equation. And here it becomes different, because in this case we do not have a constant interface temperature, and also heat will penetrate to the core of the meat, which means that it will not be equal to the ambient anymore, as we saw for task 1. So we start with the boundary condition at the interface, and to determine this, we will set up an energy balance at this interface. So heat will pass through this surface, which is transferred by use of convection, but at the same time, an equal amount of heat is being transferred by use of conduction. And this balance is not for a volume, but for a surface, so we do not have any internal energy within this domain. So we find this energy balance for the interface, and we know the standard expressions for heat transfer by convection and conduction, which we'll plug in. Then we can do some rewriting, and we'll find our first boundary condition. Then we need a second boundary condition, which we'll set at the core of the meat. In the core we have symmetry, which means that the slope of the temperature over there should be horizontal, which we'll state by setting the gradient at that position equal to 0. As said before, the meat at the beginning has a homogeneous temperature equal to that of the ambient, which we'll use as our initial condition. Now we have all conditions, which brings us to solving the equation. These conditions are identical to the ones that are used in the Heisler diagrams, which means that we do not have to do the entire derivation, but we can use these directly from the formula sheet. To determine the time t, we have to find the Fourier number. To do so, we need to determine the dimensionless temperature and the Biot number. For the dimensionless temperature, Tm equals the core temperature, which is 59 degrees Celsius in our case. Ta equals the ambient temperature, which is the temperature of the oven. And To is the initial temperature, which is that of the ambient when the steak has been cooled. Plugging these numbers in yields a value of 0.6 for the dimensionless temperature, so we can draw a horizontal line at that position within the Heisler diagram. For the Biot number, we need the heat transfer coefficient, half the thickness of the steak, and its thermal conductivity, which yields a Biot number of 0.5. And with this we can find the intersection between the dimensionless temperature and the lines for the Biot number, which is over here. And if we draw a vertical line over there, we'll find a Fourier number of 1 in this case. We can rewrite the expression for the Fourier number and make T3 while plugging in the thermal diffusivity and all the numbers that we know. Doing so eventually yields a time required of 1011 seconds. For task 3, we're asked to make a sketch of the core temperature as a function of time. As said, during the broiling process, heat does not penetrate to the center of the steak, so in this period the temperature will always be equal to that of the ambient. But as the temperature near the surface is higher than in the center, after some more time, eventually heat will penetrate to the center of the steak, and therefore it will heat up a little bit in the core. But if time moves on, all heat added during the broiling process will be lost again, and the steak will reach its homogeneous temperature equal to that of the ambient again. Then the steak is put into the oven, but as it takes some time for the heat to reach the center, at the beginning nothing will happen to the temperature. At some point in time, the steak will heat up until it reaches the desired temperature of 59 degrees Celsius, and finishing in the oven is done. It is important to note that the slope at the end cannot be horizontal, because heating was still going on and there is still a big temperature difference between the outside and the center of the steak. The fourth task is similar, but now we have to make the same sketch for location 1. It takes a little bit of time for the heat to reach location 1, so at first the temperature will be horizontal until it starts to heat up. At the end of the boiling process, it will reach the desired temperature of 250 degrees Celsius. But if time moves on, the temperature at the surface is a bit higher than at location 1, so some heat will move from the surface to position 1, and the temperature will still increase a bit. And then cooling will happen until it gradually reaches the ambient temperature. It is important that it is drawn with a slope that decreases until it becomes horizontal. This is due to the fact that the temperature difference between the ambient and position 1 becomes smaller and smaller over time. Then finishing in the oven happens. The heat requires a bit of time to penetrate, and if this has happened, the temperature starts to increase. It will increase gradually with a decrease in slope that becomes horizontal when it reaches the oven temperature. The principle is the same as we saw for cooling, which is caused to a decreasing temperature difference over the course of time. If the temperature has reached the oven temperature, nothing will happen anymore and it will remain equal to that of the oven.